Please welcome to the stage Dr. Matthew Wilding, Dr. Stephen Kuhn, Dr. Dan Wallach, and Dr. Howard Shrobe.
Good afternoon. I'm Matt Wilding, and I'm here to, I have the privilege to introduce the afternoon speakers today. Kathleen Fisher this morning talked about what formal methods is, rigorous mathematical approaches that provide guarantees about computer-based systems. And there are a lot of examples of using formal methods today. I've got three here. One is in the midst of hardware development. Today is very often used in using hardware description languages that are compiled to actual implementations. And it's routine now to equivalence check the optimized compiled hardware image to make sure that you haven't messed anything up. An absolute, almost you have to do it if you're using hardware description languages today. Another example, and this is one that's you'll hear more about, and you've already heard some about, system engineering, where vehicles are able to be engineered and architected in a way that allows us to make sure that the important things are protected on the vehicle. And then finally, a third example of using formal methods is applying them to mixed reality systems, to augmented reality systems, where we're modeling people and systems and making sure that people are protected against potential adversaries. These three examples are very different domains, very different properties, very different models that you're reasoning about, and also very different in terms of the maturity of the approach. So in the case of mixed reality, it's very much an experimental work that's going on at DARPA. Kind of not really ready for prime time yet, as we're still figuring out how to model people and how to figure out what properties you really want to show. The system engineering work, on the other hand, has been shown. You might call it pioneering, but it's been shown to work. There's been examples of using the tools. The risk has really burned out of it, and we're looking for adoption widely throughout the DoD. And then there's examples like the hardware development, which is absolutely standard. Again, you cannot imagine building something where you're not doing an equivalence check to check the tools that you're using. And so very different levels, standard, pioneering, experimental. Most of today is focused on the standard and in particular the pioneering efforts. The experimental efforts we'll talk about as we look forward a bit, but it's not, in some ways, it'll be much harder to adopt. You're more focused on pioneering and standard today. There's a large number of formal methods examples. Here's at least some samples. Not only do these formal methods tools have kind of different levels of how ready they are to make a big impact, but they're also used throughout different stages of development. So, for example, architecting, where you're early in the development of a system. One thing that's now more and more being done is proving things about the protocols to make sure they have the right cryptographic and other kinds of properties. That's kind of early when you're architecting a system, you're worried about those kinds of things. As you get further along and you're implementing, another thing that is being done somewhat in a pioneering way still, but is increasingly being done, is showing information flow analysis of software to make sure that, in fact, things information is flowing in a way that you're expecting it to flow. And this is particularly important in some security critical kinds of applications. And then in the deployment, I thoroughly enjoyed the talk we heard this morning from Amazon. The network configuration kinds of tools are increasingly being standardized and are kind of, if you will, sort of at the end of the development process. So when you're looking at different kinds of formal methods tools, in all these different categories, lots of tools, lots of models, lots of guarantees that are potentially being addressed, you want to be sensitive to which things are ready to be used, and there's many of them. And then there's a few experimental things that DARPA is still doing and hopefully will be ready in a few years. And that it can be used in many different ways during the development process. So the presentations today hit many, especially of these pioneering kinds of efforts where we think the risk is mostly out of it and it's ready to be brought and made into a huge, impactful technology in a lot of different ways. We're going to start off with Steve Kuhn talking about accreditation, and it was already mentioned today that authority to operate is a big deal, and it's something that, that DARPA has developed technologies for. Dan Wallach is going to then talk about parsers, which are a particularly good low-hanging fruit area for really important applications of formal methods. And then Thomas Bailey from Riverside Research will talk about integrating generated parsers into an application to sort of have a kind of an example of integration of something that we're trusting into a system. Then Howie Shrobe is going to talk about separation kernels and compartmentalization, which is a really important application of formal methods that allows you to keep things separate that need to be kept separate. And then we'll wrap up with Darren Cofer of Collins Aerospace, who is going to talk about proven system architectures, and he'll show an example of several different technologies that were used to do proofs about another vehicle. So with that, Steve, I'll turn it over to you.
Thank you. Thank you, Matt. My name's Steve Kuhn. I'm one of the PMs in I2O. So for a second, imagine you're in Afghanistan. And sorry, can we go back a slide? One of your missions, one of your jobs is to coordinate technical intelligence collection across a large swath of the theater. And the capability you have today takes all of the available assets you have. But you have a capability. And you want to bring that capability in because it'll vastly increase your ability to go after more things. But you can't bring that technology forward. Why? Because you can't get the paperwork. I don't have to imagine that because that actually happened to me. So one of the things I'm here to talk about is the ATO process. So as Matt mentioned, and was mentioned earlier, what is the ATO process? For those that don't know very briefly, it's how do we get the go-ahead signal that you're allowed to use a system? But one of the key points I'd like to make is that it's application specific. So if you're talking about aviation, it's a wholly different process from cyber. Vastly different set of paperwork, which is also used by medical as well, wholly different process. And so at DARPA, program I'll be talking about, we're continuing to focus on the aviation piece, and we're looking at going forward in some of the cyber pieces. But the point is that doing this costs millions of dollars, thousands of labor hours, and it really comes focused on compliance versus security. And the point is that our paperwork is preventing the critical tech from reaching the warfighter. And on top of that, it's stopping our ability to innovate because we're having to stop developing code to get the paperwork done. So what does that really entail? What makes it so hard? The problem is the accreditation problem has become orthogonal and after the development process. And because of that, it becomes very human-centric, which inherits all the problems that humans have, right? It's unrepeatable, error-prone, non-deterministic. It becomes relationship-based, which is exactly what, with formal methods, we don't want. What does that turn into? The warfighters and users can't get the software they need at the speed of relevance. Since coming on board at DARPA, I've been talking, obviously, to a lot of program offices, and one of the things I've heard in several cases is that they're not patching the systems, not because they don't have the capability, they don't have the fix, but because they can't afford to do the paperwork. I don't think I've ever heard a better example of putting your head in the sand than that. But the point is we have these solutions. So DARPA's technologies, they're, with these formal methods capabilities, inherently more secure. They enable you to develop software, as you heard from Amazon, that's more performant, faster to deploy, and really form the basis of how do we build this accreditation process into that. And so that's what I'm going to talk about. And we automating this life cycle. So ARCOS, this is the program specifically, so automating rapid software, certification of software. So one of the things that the ATO process really mandates is you have to build that shared state with another human that what you've developed in software is safe to use. And so the reality is you're essentially dropping a library of information into somebody's lap and saying, okay, you're the accreditor, here's an entire library, I need you to learn this very quickly and make a determination of whether or not what I did is safe. Does it do what I intended it to do? And that's a very hard thing to do. So the software we built in ARCOS specifically looks at how do you help a person overcome that challenge and curate, for lack of a better term, that library of information that they have to very quickly understand and make a determination on. And so that's a step forward in automating the accreditation process. Sorry, go back one. As part of this, we worked with our partners at Lockheed on a co-sponsored prototype called CertGate that helps solve these challenges. Additionally, in the same program, GE developed a tool called RAC. And one of the things, again, curating that library of information you have to make a decision about. One of the things their tool enables you to do is understand that the key insight, depending on where you are in the design lifecycle, you often have to ask different questions of code. So if you're the data scientist or the frontline development engineer, show me how does a formal analysis of my change impact this code? What's the blast radius of my change? What else have I broken if I change this? Or what have I not? But that's very different from your manager. They need to see a dashboard of where do I stand in this accreditation process? What have I got done? What don't I have done? What test reports do I have today? What do I need to work on next, right? And that's very different from, obviously, the certifier who wants to see the total picture. You know, where's all my test information? What has it done? And this tool allows you to essentially time shift through that development scale and see, depending on your scale or depending on your role, the information you need to help you move through your job faster. And one of the best parts is this tool is available open source today. So it's something you can actually go download and use in your programs to help with this accreditation problem. So I encourage everybody to go out. The link is right here if you want to take a photo, and you can use this. And forthcoming, we'll have a website with some other tools from the program that are available for use as well. As you heard from Oren and Kathleen earlier, we're partnering with the United States Air Force to continue these accreditation advancements. And we're working internally with them on this capstone to show and quantify these impacts of these formal methods tools. So how can we integrate these more quickly and quantify the impacts to demonstrate that cost savings? One of the key questions we're often asked is, well, as Oren was mentioning, the organizational inertia. Are the accreditors on board? And so far, the ones I've met with have said yes. They're really inspired by the potential this holds for helping, really for them to do their job faster, because they want to get these technologies out there just as badly as we do. So those are the tools we've built and you have available today. But as Rob mentioned earlier, this is DARPA. We want to swing for the moon. So where are we going next? I want to kind of pull behind a curtain a little bit and mention what we're doing next. So continue to automate the labor-intensive aspects of accreditation. How can we make it even better than the tools we have available today are? And the goal of that is that the accreditation becomes part of the development process. It's not some distinct things. I like to say internally, how are we hiding the vegetables? Can we bake them into the process so they don't know they're there? If you sneak them in, are they going to be willing to eat them then? Because you don't want those frontline developers. It's just a tool. They want to use it. They want to get the job done. They want to write code. They don't want to think about SAT solving, formal methods, HOL languages. They just They want to build it. So how do we bake those in? To do that, I was kind of had to take a step back and understand, well, what drives that process? What makes it so difficult? And really, it's the disparity. If you think of it from a formal methods standpoint, the ATO is asking you to basically back up to prove your claim. Did you do what you specified? But the challenge is to do that means you need to essentially set in stone and stop what you're doing in development. As we know from the development process today, it's a continuous process. Has anybody in the room ever been successful asking the engineers to stop and wait for the specification to be done before they go off and start coding? If you are, I'd love to talk to you. So the real challenge is how do we bake it in so that that becomes a continuous process with these formal methods tools so that you don't have to stop. And continuing on from there, it's not just the process of development, it's the process of engineering, it's the process of specification. Because all three processes, not just one loop, it's really 3 loops. And each of these loops has a different time scale. Each is iterative, asynchronous, and irregular. We need the tool, using formal methods, we can link these different processes together so that at its core, they'll keep the accreditation process in sync so that your engineer can see changes your developers made, so that your specifiers can see you've actually implemented what you said you would specify. And if we accomplish these with formal methods tools, the accreditation paperwork will essentially become baked into it. It won't be a separate process, so that we need tools that operate at the speed of mission, not at the speed of paperwork. And formal methods can allow you to do this by having this baked into that design process so that it becomes inherently repeatable, verifiable, where you remove that human element, that relationship piece that's non-deterministic, so that you can know, oh, I wrote a piece of software, I know it does this, it only does this, and what do I need it to do, and then bring it forward. And when bringing it forward, boom, it's accredited, it works, get it out there. And in my view, formal methods can help create that repeatable process. Why do I think we can do that? Next. I'm pointing at the screen as if that's going to make it move faster. You heard this morning from Kathleen and Oren, and you're going to continue to hear from some of the other PMs just shortly about our portfolio of formal methods tools. They form the basis of creating these linkages between the design lifecycle elements. These programs really laid the foundation for revolutionizing the way software is not only accredited but developed. Because imagine if your engineering model is automatically updated when the developer makes a change. How powerful would that be for the way you write software today? And conversely, imagine if the engineers doing the modeling discover something you didn't realize, an oversight that it opens up in the specification. And then your specification then gets automatically updated to incorporate those changes as well. How much quicker that life cycle for software development would be. So in summary, please download the Arcos tools we developed today. They're available for use. They will they'll help you get over some of the technological barriers with ingesting that mountain of paperwork to get over those accreditation challenges. Our partners at GE and Lockheed are using them. And we're continuing to use them with our partners in the Air Force and experimenting on them with the capstone effort. And the future work is going to continue to enable this automation so that the resilient systems can obviate the need for this human-centric process and get us towards software that can perform at the speed of mission. I thank you for your time. I'd like to introduce Dr. Dan Wallach, who's going to talk to you about parsers.
Thank you, everybody. I asked for them to have me lowered from the ceiling on a wire, and I'd have cool music and 5/4 time going, but unfortunately, apparently, we don't have the hard points on the ceiling for rigging. Really disappointing. Anyway, my name is Dan Wallach. I'm going to be talking to you today about parsers. So what's the deal with parsers? Why are we focusing on this one interesting bit? Well, we have complicated data formats that we live in. In the civilian world, we could talk about something like Adobe PDF, which is a voluminously large specification, covers thousands of pages of explaining all the different options. And where you have complexity, you have bugs, and where you have bugs, you have security issues. Unsurprisingly, there have been a large number of security issues involving and around Adobe PDF. And if that applies to PDF, that probably applies to all the data formats used in the military as well. So what can we do to help? Well, when you have a complicated data format, the thing that reads that data is called a parser. So the question that we're asking is, how can we improve the engineering of this piece of the code? So I'm a computer security guy. From a computer security perspective, what a parser does is it has bytes that come in, perhaps from a network, perhaps from a radio, and what comes out is some potentially sensitive internal data structure. What that means is the parser is the attack surface. The parser is the thing that your adversary looks to first, because that's the first software that touches your data. So you'd better get it right. And you might find it wildly unsurprising that when C and C++ developers do it in an ad hoc way, of course they do it wrong. A famous example of this was a decade ago's Heartbleed vulnerability, which was an OpenSSL feature where there was a length, a number, an integer length, and then some amount of bytes. But the amount of bytes and the length field didn't have to be the same. And so an attacker could put a big number here and a small length there, and they could arrange to read out arbitrary memory from your web server. So the attacker could read out your secrets, read out your keys, read out all the bad stuff that you don't want leaking. So the challenge is, how can we help the developer avoid taking these little shortcuts? How can we eliminate this entire class of bugs all at once? That's the parser. That's the piece we want to fix. So I'll take a slightly different view of it. This is Noam Chomsky from the 1950s, and he helped formalize what we think of today as formal grammars. So what's a grammar? A grammar is a set of rules that accepts a language. And a language, messages that are in the language should be accepted. Messages that are outside the language should be rejected. So that's it. That's what a parser's job is. It's a definition of a language. How hard could that be? Of course, Chomsky gave us a lovely example. This is a quote, "Colorless green ideas sleep furiously." It's grammatically correct English, and yet it's still nonsense. So just because you've correctly parsed something doesn't mean you're done. You still have to analyze the message to make sure that it makes sense in ways that just the parser alone might not cover. But if the parser can reject malformed language to begin with, that gets us a lot closer to a better security. So from a pragmatic perspective, this notion that I need to go from internal data structures back to bytes, back to internal data structures, this is something that computer scientists writ large have been working on for decades. An early general purpose example of this is ASN1, which comes from the telephony people, and they tried to solve every possible version of it. You want compressed packed data structures? You got it. You want unblown up human readable data structures? You got it. And by trying to solve every problem, they solved no problem well. And some of that showed up in our cryptographic standards, which is X509 uses ASN1, not the greatest. Google decided to reinvent the wheel and do it in a pretty good way. So if you've heard of Google's protocol buffers, those are a very robust version of the same idea, where you write down an abstract specification of the messages, and then it's the job of a formal tool to process that abstract specification and give you all the serializers and deserializers to help you deal with that. But not everybody wants compressed, tight data structures like what Google protocol buffers give you. So instead, we have a hugely popular set of human-readable data structures that are easy for you to write by hand. So you've probably heard of XML, JSON, JavaScript object notation, YAML, and there are several others. These are widely used because they're easy, they're simple. But even then, that's not enough. There are always particular markets, particular requirements that require custom engineering. A simple example is if you have streaming audio and video. Your television, when you turn it on, doesn't get to go back 20 minutes to the start of the show to start parsing the video. It has to be able to jump into the middle. So that means that streaming protocols have extra requirements for synchronization and error correction. Similarly, back in the bad old days of floppy drives that many of us remember, Microsoft Word and Office and PowerPoint of the day tried to engineer around our terribly slow floppy disks by having fast save. I'm putting scare quotes around that on purpose. Fast save, you would delete, 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 save. It didn't want to rewrite the whole file on disk. That would take too long. So it would just append some changes. And what that meant was that you think you deleted it, but it's still there on disk. This was great if you're into forensics analysis, but maybe not so great for everybody else. So file format is, file format design, which is to say parser design, they're kind of one and the same. There are all sorts of interesting twists and complexities to getting it right. Okay, I will briefly become a functional programming nerd. For those of you who are not software engineers, don't panic. Parsers are algebraic data types. You might be like, what? And what that means is that we can construct software by treating parsers as objects that small parsers can be combined into bigger parsers. And this is a great way of specifying a parser, and we have tools that can then efficiently run with that. So the code on the right is an extract of a parser. So it's written in the C programming language, and it's using something called Hammer, which is a formally verified parser generator combinator library. And on the left, I have a small chunk of the JSON JavaScript object notation specification. So I've highlighted the part that says we have values with commas between them. So we have, the comma is a separator, and then we have multiple values. And there's one line of code that expresses that concept. It's that h_set_by. So we want to create a comma-separated list of these values. So with one line of code, you can express that concept. Similarly, this h_middle expresses the idea that I have something in between two other things. So I have an open bracket, I have the thing, and then I have a closed bracket. So we're taking the parser we just built with the comma-separated value, and we're saying that, but a bracket before it and a bracket afterwards. And this, in turn, gets put inside yet another parser. So it's parsers inside parsers inside parsers, parsers all the way down. When you look at this style of coding, the software looks a lot more like the way you would write an abstract specification, just in English meant to be read by humans. And what's notably not here is you don't see any error handling code. But remember, I said that a parser accepts a language and rejects everything out of the language. By having a good, rigorous specification of what's in the language, we also, kind of for free, get a very robust rejection of anything that's outside the language. So if you want to learn more specifically about parser combinators, that's a nice link to an example. There's a ton of stuff online about this. And you name the programming language, there's at least 2 or 3 parser combinator libraries that you can use with it. But of course, I mentioned that it's not just about getting the grammar right. We also have this notion of static semantics. So the Hammer parser generator combinator library has a bunch of features to help. This is a small extract from the National Imagery Transmission format. That's like how cameras in orbit will send photos back to the ground. There are a lot of details. And in this case, there's a rule that says if this particular field happens to have this particular 6-digit number, then something else over there had better be true. And there is a way that you can write these kinds of non-local rules that says that this thing implies that thing. So it's not just about the grammar. You can also express these non-local rules and relationships. All right, but how hard is it to do this for real? So I decided to ask an LLM because that's a hard question. So I'll let the LLM answer it for you. So I said, hey, Google, Gemini 2.0 / deep research, find all the CVEs for popular C and C++ JSON parsers and categorize the vulnerabilities for me. And it actually ran for 30 minutes, which is, on the one hand, wow, that's a lot of compute these days, right? And what it gave me was really interesting. It gave me these nice tables, and I checked. These CVE numbers are legit. They're not hallucinations. Like, I didn't believe it. I had to go and check. And it nicely broke them down. So we see that popular JSON parsers are incorrectly handling Unicode strings. We see that popular JSON parsers have integer underflow and overflow, denial of service. And big surprise, if it's written in C and C++, it's going to have buffer overflow vulnerabilities of various sorts, lots of them. For some reason, a Rust bug showed up in my list of C and C++, but it's unsafe Rust, so maybe it belongs. I don't know. Not hallucinated, but also not really belonging. Anyway, lots and lots and lots of bugs that only happen in handwritten C and C++. If this had been written in Hammer or any other parser generator, none of these bugs would have been here. And of course, various kinds of input validation bugs, uncaught exceptions, null dereferences, out-of-bound reads. None of these things would ever happen in a machine-synthesized parser. Oh yeah, and denial of service. Okay, so you might say, let's use a safe programming language. That'll solve all of our problems. We're going to rewrite it in Rust. Yeah, which I support, by the way. It would have solved the Heartbleed vulnerability. It would have fixed many of these bugs. But nonetheless, important security decisions are still made early in the parsing process. And there are many downstream security vulnerabilities that if you're not careful, your parser might still open up for you. So things like SQL injection and cross-site scripting, if you squint at them, you interpreted a piece of text as if it was vanilla text when it was actually code. That's sort of a parsing problem, and getting that right is something that you should be thinking about early in your engineering process. So if you solve the parsing problem, you're not completely done. But if you do your parser right, you can help with this class of bugs too. So for the rest of my time, I'm going to be telling you about SafeDocs, which fits here into Matt Wilding's taxonomy. SafeDocs was a DARPA program that tried to solve this general purpose problem of I give you a spec, and my spec is stupendously complicated with non-local issues. That something up here in the table of contents affects what happens way down there far away. And so what the SafeDocs performers did was they built a wide variety of tools. I showed you Hammer earlier. If I had more time, I would show you all these other different parsing tools and all the ways that they let you express complicated relationships that are not just traditional recursive descent grammars, and they help you get it right. But the work never ends. Right now, today, we have a DARPA program called vSpells. I'm the program manager for vSpells. And one of the challenges that we've given our performers in phase 3 of vSpells, so first off, wait, what's vSpells? vSpells is analyzing code, whether it's source code or binary, at scale. Millions, tens of millions, hundreds of millions of lines of code. So tooling to do general purpose software analysis. We gave them a challenge for phase 3. And the challenge is, there's a parser in there somewhere. Go find it. And if you can find it, that would help us to, rather than, today, I say, here are SafeDocs, go build yourself a new parser. Tomorrow, someday, wouldn't it be nice if I could say, here is SafeDocs, and here is an extracted version of the parser from your original code, and we're going to help you make sure that the new parser you write and the old parser are parsing the same language. That would be very helpful. That would help you modernize your code more rapidly, more effectively. So that's what we're working on. So while we were doing this, one of the teams that's the BAE and Purdue team, they said, that sounds fun, but could I find bugs that way? Which is always a fun question to ask when you're a security person. I wonder if I can use that to find bugs. And so what they did is they said, what's a good source of input that we can find lots of bugs quickly, where parsing is like essential to it. And they said, how about the Open 5GS reference source code? So 5G is the standard that all your cell phones are speaking today, and there is a large body of open source software that implements all of the 5G radio specs. And the specs themselves are also online. So they said, let's use a little LLM secret sauce to read all these human-readable specs. Let's look at the code. Let's put it into a giant blender, and bugs. So they were able to, all but one of them were confirmed. So we're seeing that these are each horizontal row is a different part of the 5G stack, and you can see how many pages there are of specification. If you as a human were trying to grind your way through this, it would be sleep-inducing. But if the tool can do it for you, your ability to validate that the bugs that it found, that's much less sleep-inducing and much more fun. Well, fun for you, maybe not fun for the Open 5GS source code maintainers. Anyway, so some things I would like you to take away from today's talk. I would like you to take away that parsers are the attack surface of your code. The vulnerabilities that the adversary is going after all start in the parser. If you get the parser right, you have a hope. If you get the parser wrong, you're doomed. But luckily for you, parsers are something that computer science theory people have been thinking about since the dawn of computer science, which means we have a large body of theory to reason about formal languages. And that allows us to have very sophisticated tools where the formal methods are under the hood. You, as a programmer, are simply writing down a specification in a nice, convenient, high-level format. And a tool like Hammer or Parsley or Daedalus will deal with the parsing for you. And oh, by the way, not only are they more, you're not going to have all of these security bugs to worry about, they're often substantially faster than handwritten parsers. So you get extra performance. You come for the security, stay for the high performance. As an extra bonus feature, let's pretend you have a bunch of different vendors that you all want to talk the same protocol. Let's say you have something like Link 16, where multiple different fighter jets need to be able to communicate with each other. Wouldn't it be nice if you could make sure they were all speaking the same Link 16 protocol? So that way, there aren't subtle differences, and they're more likely to interoperate together. And then you could have that spec, the formal spec, be part of the Link 16 spec, and then force all of your vendors to cooperate in a nice way. Well, if you write down your parser using one of these SafeDocs tools, now the spec that you're requiring all your vendors to cooperate with can be formal as well. So not only do you get to write, not only do I get the security benefit, and not only do I get a performance benefit, I also get a standardization benefit. 3 for 1. So you have multiple deployment choices. You could tear out your old handwritten parser and replace it with a SafeDocs parser. That's preferable. But perhaps you have an ATO issue that prevents you from tearing out your legacy parser. You could use SafeDocs tools to build a firewall in front of your legacy tool that you can't touch for various reasons. We're actually pursuing a version of that today as a capstone project with the US Navy submarines. So high-level description, a US Navy submarine on the inside is a very modern design, networked, really cool. Can't tell you the details here, but it's really neat. But they also have, let's call them legacy devices that they can't change. And so you need to connect the legacy parts of the submarine to the modern parts of the submarine. So today we're working on using SafeDocs to build a firewall to protect, to create extra compartmentalization inside our submarine. So that's work that we're doing today using SafeDocs. Thank you very much. And we have a demo. This is not a submarine. Not for long. But it has the same kind of SafeDocs technology. And with that, Tom Bailey at Riverside Research. Take it away.
Perfect. Thank you, Dan. Hello everyone, my name is Thomas Bailey, and what I want to show you here today with this drone is how we can prevent this from happening to your operational platform through the application of these SafeDocs technologies. Now, before I get too far into the demo, I need to back up a little bit and explain what it is exactly that you're seeing on stage with me with this adorable little drone. What you're seeing here is a representative system that's communicating via an interoperability protocol developed by Army C5ISR. Whereas SafeDocs originally targeted the PDF specification, we now have the ability to extend these SafeDocs toolings over to these operational platforms and target real steel DoD specifications such as those developed by the Army. C5ISR developed this protocol in order to enable joint mission scenarios through Army and Air Force. And that's exactly what we're showing here today. On our sensor system, we're running a Raspberry Pi that's using that Army C5ISR radio frequency standard. It's got our secure parser that we're showing via this little box. Obviously, in a real system, this is something that you'd see abstracted away. Now, what this does is it ensures that all of the information coming into that system at a bitwise level is exactly conformant to the protocol specification developed by Army and agreed upon by the Air Force. Now, we can turn our parser on and off to show what it looks like when an adversary seeks to corrupt this communication. On the other end, we have our ground station, a simple WASD keypad that allows me to move the drone up, down, left, and right. And you can see that when I do so, I get two blue lights. And what that says on the drone is that I received a known good packet, one that is conformant to that Army Air Force specification. And the second blue light is indicating that I did indeed pass that on to the drone system and move the camera accordingly. But obviously, cyber is looking to defend against adversaries. So in the life of a good packet, it's simple enough for me to assume the role of the controller, input the command onto the WASD keypad, which is translated via the Raspberry Pi and sent over RF as a MORA data message. That's the protocol I talked about earlier that was developed by C5ISR. As that's broadcast out into the air, we then receive it on the other end, on the drone sensor system, and break that down into its raw binary. With the secure parser on, we can inspect at that bitwise level and make sure that no singular bit doesn't match the conformance that we're looking for from the protocol specification from the Army. And then, and only then, do we pass that information on to the sensor computer, knowing that it is formatted correctly and can be trusted, reducing the ability for an adversary to take advantage of memory corruption vulnerabilities, eliminating entire swaths and classes of that vulnerability. As such, we're able to move our camera as I'm showing you with the keypad here. We get our two blue lights and we can move our camera up, down, left, and right however we please, both with the parser on and off. But things look a little bit different in the life of a bad packet. I brought this Flipper Zero, commodity hardware that anyone can buy online for about $150, and it gives you a variety of hacking capabilities. What we used it for was to sniff that communication between the Army ground station and that Air Force drone and re-upload that as a binary, taking the role of an attacker and crafting a malicious packet that we can then re-upload to the Flipper Zero in order to impersonate that ground station and send maliciousness into the air. These are real attacks that we see in contested environments today, where adversaries can buy this cheap commodity hardware, attach more powerful antennas to it, point it up into the sky, and cause the drone to do something that it's not supposed to do. On the other end, the drone receives that information not knowing whether it's good or bad, only knowing that it's a message that it should be ingesting. Now, with our secure parser turned off, that information is immediately passed to the sensor computer, but there's maliciousness hidden in that raw binary that we then break down. And this can cause a variety of different attacks on the system, such as denial of service attacks, slowdowns, or even worse, harm to the warfighter. And so you'll see here I have my secure parser turned off. And when I use my Flipper Zero and point it at my drone, I get some amount of maliciousness to occur. And I don't know about you, but I typically want my drone pointing exactly where it's supposed to be. And as I launch this attack again, look very closely at the lights. So you'll notice that we get a yellow light on the left, but a blue light on the right. And what that's indicating is that we received a malicious packet that we should have rejected, but we didn't do that. Instead, we sent it on to the sensor system since it's not running through that secure parser. And that blue light indicates it was accepted by the camera sensor system and causes that maliciousness that you saw. But SafeDocs to the rescue. We took that Hammer Secure Parser Combinator library, the same one talked about by Dan, and applied it to this specification so that we have a parser that enables correct by construction code. The code that is ingesting all of the information being received by the drone system can make sure that all of the information you're receiving is well trusted and formatted. So with our parser turned on, the story looks pretty similar at the beginning. We receive that information as we would normally, but before passing it on to the sensor system, we check on that raw binary to ensure that every single bit is conformant to that interoperability specification. And only then would we send it on to the sensor system, rejecting any malicious packets. And I can show that here by flipping our drone on. So I can turn our secure parser on here, and then when I launch this same attack from our flipper 0, you'll notice we get 2 yellow lights. What that's indicating is that we received a bad packet that we should have rejected, and we did indeed reject that. And that's that Hammer parser at work, ensuring that all of the information we received is exactly conformant to the specification, yet still allowing our known good controller to control the drone sensor system as they want. So as I show the full system diagram, I want to walk through one more time what it looks like for all of this to happen on the drone. So with our parser turned off, while I, the known good controller, can still move the camera system up, down, left, and right, an adversary can use commodity hardware to compromise the drone and compromise the warfighter's mission. But at the flip of a button, or in this case, the turn of a switch, I can enable that SafeDocs Hammer Secure Parser, one that is ensuring that all of the information I pass to the drone is known good and well formatted, rejecting that maliciousness at the edge of the drone before it ever has a chance to reach the sensor system, while enabling correct mission scenarios for my warfighter. And so why does this matter? These adversarial injection attacks are real. We encounter these in contested environments today and will continue to encounter these so long as these protections aren't in place. 80% of vulnerabilities can be classified as memory corruption vulnerabilities and can be protected through the application of these types of secure parsers. And not only are they applicable to drone systems like the one I have on the stage, as Dan mentioned, we're applying these same technologies to naval submersible platforms, and we will continue to apply them across DoD platforms and industry. No longer is SafeDocs limited to the PDF specification. And in fact, I implore you, if you see use cases for these sorts of technologies for your operational platforms, I'd love to chat, because these technologies are ubiquitous across platforms, both in DoD and industry, and deserve to be recognized for the protections that they can provide over traditional input handling vulnerabilities. Thank you.
Hi, I'm Howie Shrobe, Program Manager in I2O, and I'll be talking about separation, kernels, and compartmentalization. Now, the fundamental problem that we're trying to address with these technologies is how to protect mission-critical software from all the other software that happens to be in your system. When you load a program into your computer, you wind up loading in libraries, and those libraries wind up loading in more and more libraries. And so there really is no small system. They're all bloated up with lots and lots of other software, much of it opaque, none of it is yours, and you rely on that. The problem is your mission-critical software is sitting there too. On top of that, they're all running on top of an operating system, which is also loaded with vulnerabilities. So how do we protect the mission-critical part of our system from all these other parts that are doing useful things, but are also offer vulnerabilities? So one way we think about this is an analogy. Ships used to be built in the old days with one big ship, one big hull, one big shot of underneath the waterline would sink the ship. That's not the way we build ships today. We build them with many, many compartments separated by bulkheads so that even if the hull is penetrated and water starts coming in, it doesn't get everywhere. It doesn't get to the mission-critical parts of the ship, and therefore you're protected, even though you have exploitable vulnerabilities. Now, we're not building ships, we're building software, but this gives you a good model of how to think about what the problem is. And one lesson that's going to run through the rest of this talk is that architectures matter. Ships used to be architected one way, they're architected a different way today. That's better and more analyzable. Now, one thing to keep in mind is that there are many things that we've talked about already today, such as memory safety, which eliminate a large class of vulnerabilities, or at least prevent them from propagating to the point where they can get to the crown jewels of the system. Compartmentalization is another one of those, and what this chart is showing is the result of a study done by people at MIT Lincoln Lab, and me, to be honest about it, which showed that the combination of these two technologies, memory safety and compartmentalization, which are essentially siblings, would prevent a large number, 87%, of the critical attacks on the Linux kernel. There's a residual that's still worth worrying about, but with just these two technologies, we can prevent these attacks from propagating from point of initial penetration to exploitation. It's worth thinking a little bit about, well, how did we get here? And the answer is, long, long ago, not long enough that I wasn't there, computers used to be really big and have almost no computing power. A room full of computing technology had less power than my watch. And so what these systems did is they ran one system at a time, batch processing. And as they got a little bit more powerful, we said, okay, we can actually fit more than one thing in there, but we're going to make it seem to them as if it's the only thing there, that they own the whole machine. And one technical thing that was done was to build into the hardware what's called the base address register, or at least it was on the system I worked on. And that just set base and bounds that this program could not access outside of. Now, these machines were very useful in their day, but frankly, submitting large decks of cards and waiting for a dump to come out on the line printer was not the most fun way of computing. And so in 1963, DARPA sponsored a project at MIT called Project MAC. And MAC stood for multi-access computing. The idea was, let's create a computing utility that many people could share and use the same way we all share other utilities. And that meant that we were now entering an era of multi-access computing in which it was an interactive experience. Now, to tell you a little story, there was a graduate student in the lab at the time named Jerry Salter, who went on to become a full professor at MIT, and wrote one of the most seminal papers on computer security, usually known as the Salter-Schroeder paper. And what Jerry did was, like many graduate students, he decided that before he could write his thesis, he needed to write tools to help him write his thesis. And so he created one program called Typeset, which was an editor, and another program called Runoff, which many of you know its descendants, which was the formatting program. And these were so useful that everyone else wanted to use them too. And this brought up the question of, in this interactive context, how do we share the things that Jerry wants to share without sharing the things that he doesn't want to share? He's perfectly happy for you to use his programs. He doesn't necessarily want you to access his data. And so we invented new technology, which eventually became virtual memory, pioneered in a successor project called Multics, which became the prototype out of which Unix emerged. So this idea of virtual memory introduced in Multics, which let you share memory very carefully, then became ubiquitous. We all assume it's there today. But there are problems with this. And one of those is we now have a big complicated mess as our operating system. For one, by the time we got to Unix, we got to the C programming language, and people have said enough about that before. It opens many vulnerabilities because of lack of memory safety. We need to know in this system, can we really formally guarantee that unattended sharing doesn't occur? And in any event, what do we mean by unattended sharing? What is our sharing policy? On top of that, the operating system operates with unlimited privileges and itself has many vulnerabilities. So this was great from the point of view of usability, but it's introduced us to an era in which many things are vulnerable. So what could we do about that? Well, in 1981, John Rushby introduced this idea of a separation kernel. And it's a coarse-grained distributed system model for controlled sharing. And the idea was, if we think back to that batch processing era where everybody thought they had their own machine and they were isolated, Let's create a system in which that really is the reality, so that every system that's running in the same computing system, every program that's running there, is completely isolated from all the other ones. And it's the role of a small kernel to make that be true. And the only interactions these things can have with one another is by passing messages. Now, this model, which I'll talk about just a little more, involves many formal methods. If you want that kernel to be trustworthy, you want it verified. So theorem proving becomes involved. These messages that are being passed back and forth, I don't need to really emphasize again that you really want to make sure they're correct messages, that they're parsed appropriately, and that they don't introduce problems. And to do that, we use proven software generation techniques like parser generators. So with this framework, we then get to a situation in which we can isolate our mission-critical software in one partition, have all the mean greenies and the scary and hairy code over in other partitions, and be comfortable and sure that those things that we don't trust cannot possibly affect the things that are mission-critical. The key to that is a small verified kernel, the separation kernel, and careful handling of the message processing between them. In a while, Darren Cofer from Collins Aerospace is going to talk about work that was done in the HACMS program. Kathleen talked about that earlier today. I think even used the same slide. And that was a system that used exactly this model, where the separation kernel, SEL4 shown there, was in fact isolating the parts of the system that were not trustworthy from the parts that could interact with the parts of the system that we needed to trust. So let me just say a few things about SEL4. It was not a DARPA product. That's fine, we're trying, but there are many things about it that are very important. So one of those is that it has a formal proof that it correctly enforces access controls. Secondly, it has a proof that it implements what's called non-interference for information flow. And Kathleen told me to make sure I had a bottle of water nearby because I've had a cold. Now, as I said, separation kernels are typically small. SEL4 is about 10,000 lines of code. But it's accompanied by 480,000 lines of proof code. This is guidance to an interactive proof checker. The design and implementation of SEL4, the initial implementation, was 2 programmer years. The verification effort was 11 years of PhD-level formal methods experts. And you look at that, that ratio is rather striking. Now, this is an exquisite artifact. And you might look at these numbers and say, oh my God, I'm never doing that. But the good news is you don't have to do that because it's already been done and it's usable. If you need to do this for something else, we're developing tools to help you do that, like the tools in the Provers program. So here's a way to think about how you would apply this level of technology. You start off with your original monolithic mess. In there is Snidely Whiplash and your crown jewels. And what you want to think about is how to separate that into all the different pieces that might have Snidely Whiplash in it and the part that has your crown jewels. I don't know if I'm dating myself. Snidely Whiplash is a Rocky and Bullwinkle character. Now, your separation kernel allows you to partition all of these off, one from the other, so that all of these things with the problems in it can't get to the crown jewels. They may die, you may need to restart them, but it doesn't matter. And the second step is that you formally specify the grammars for the messages that can be passed between them, and you use message handler generators to generate the code that takes care of those. So this, as I said, this is technology you can use. It's there, it's open source. The URL here is sel4.systems, and it's a very good tool for this kind of application. There are also commercial microkernels that are also separation kernels. I don't think that any of them have had the same sort of formal verification done that SEL4 has, but I could be wrong. Now, in the little time left to me, I'd like to talk a little bit about what we're doing inside DARPA today, what the programs we're sponsoring, and give you a little peek behind the curtains. So I'm a program manager for a program called CPM, which stands for Compartmentalization and Privilege Management. But in contrast to this separation kernel, which is very coarse-grained, the goal here is to get a very fine-grained compartmentalization. The basic thinking is that if a few large compartments are good, many small compartments will be better. Each of those should be run with minimum privileges. The principle of least privilege applies here, which I mentioned Jerry Salter a little while ago at the beginning. He was one of the first people to state that principle explicitly, that every piece of the system should run with no more privilege than it needs to affect its task. There are two big challenges that this program faces. The first is that it has to efficiently enforce fine-grained compartmentalization, and we're using hardware support to do that. This includes both novel hardware designs, for example, the Cherry system that some of you may know about, and another effort that's going on at Draper Lab, which is being incorporated in a DoD system. There's a couple of people from Draper Labs over there who can tell you more about that work if you want to know about it. The second point is that each compartment should have least privileges. It should only have the privilege to do what's necessary. But of course, the challenge now is to figure out, well, what are those? And what should be the compartment sizes? And so the other big challenge is to do that automatically, to use automated software analysis to determine what our compartment boundaries should be and what privileges the compartment should have. Now, there's a trade-off here because the smaller the compartments, the more you're going to be switching between those. That's a context switch and it has overhead. But you get more containment that way. The bigger the compartments, the less you're going to be switching, but your containment is going to be reduced. And so it's the role of this software analysis to determine what is an appropriate trade-off point between the degree of confinement, that is, how small are our compartments, how much privilege should they have, versus how efficiently can we enforce them. Now, there is technology that's partway on the path there that you can use today. First of all, every browser you use is using compartmentalization to break apart the different tabs in your browser. You don't even have to think about it, it's just there. There's a tool called RLBox, which again is open source available. And what it does is it compartmentalizes your libraries so that they cannot interfere with the main path of your program. If there's a bug in your library, and that's where a lot of the bugs are, then it's not going to affect the main part of your program. There's a system that was developed at Lincoln Lab. These are the same folks who produced that chart I showed earlier about the role of memory safety and compartmentalization. Nathan Burrow from Lincoln Lab is here today. He has a poster. You can talk to him about this system. This is doing fine-grained compartmentalization on the Linux kernel. It can run on a number of different hardware platforms with different performance gains for each of those. And I want to mention that Cherry, which is a hardware platform that's been under development since 15 years ago when we funded the initial effort on this in the CRASH program at DARPA. I was the program manager for that too. It's now, there's a commercially available FPGA version of this, a licensable profile for an FPGA available from a company called Codicip. And that runs a fully memory safe at the hardware level system. And there's ongoing software being developed in the CPM program to do fine-grained compartmentalization in this system. With that, I want to introduce Darren Cofer from Collins Aerospace to show you some work that was done in the HACMS program that builds on these themes.
Great, thanks. Thanks, Howie. Okay, everybody, stand back. No, we're not going to fly this thing. It doesn't even have propellers on it. It's fine. So this is our very old quadcopter, and we'll talk about that in a minute. I'm Darren Cofer. I'm a fellow at Collins Aerospace, and the goal, as we've heard many times in this the talk so far, I like this picture, is from some of the coverage we had of the HACMS program during the program from Quantum Magazine. We have our sparkly formal methods that are protecting us against the evil Snidely Whiplash helicopter attackers. But if you remember, going back to 2011, when Kathleen started working on this program, that was when we first started having an awareness that, oh my gosh, all of these embedded systems that we have that we just added cool network connections to, now they are all of a sudden susceptible to the same kind of cyber attacks that our laptops and our servers and everything else are. So cars and refrigerators and printers and everything else. So the idea for HACMS was to show that formal methods can be used to build embedded systems that could be applied, in real aerospace applications that would be resilient against cyber attack because they can be proven not to have typical security vulnerabilities. And that was our team there. Rockwell Collins is what our company used to be called. We had folks from the SEL4 team at then Data 61, and University of Minnesota, and Boeing that were working with us. Okay, but how are we going to do this? So this has been alluded to already today, and this is kind of what you typically think of when you think of applying formal methods, is this exquisite artifacts approach. We're going to dedicate a team of formal methods experts to produce a comprehensive specification, do the development, verification of some critical high-value reusable components for products. And this is a great approach as long as that's what we're talking about, something that we can amortize that investment again and again and again and again and use as a foundation and build on it. But the other side, so think about the dial that Kathleen showed, is essentially invisible formal methods, or nearly invisible, where we integrate highly automated formal methods tools into our existing workflows and development processes or model-based development environments in a way that they can be used by non-formal methods experts. And this is especially important for us in our industry because our systems are very heterogeneous. We have in Collins, we make everything from the toilets in the back of the airplane to the all the cool flight control equipment in the front of the airplane and everything in between. And every one of these things is different, has a different team that builds it. They use different tools and ways of specifying their requirements. So it's important for us to be able to inject formal methods into their processes where they are today. So these are two equally successful and valuable mechanisms for transitioning formal methods into processes in industry. And they're based on typically different tools. The very dedicated use by formal methods experts tends to focus on theorem provers. The high level of automation typically is model checkers, but more and more both of these rely on sophisticated solvers, and we have model checkers that can emit proofs of what they have found, and we have theorem provers that rely on the same solvers that model checkers do. So there's less and less separation between these two, but the key is that there's a lot of automation that we can leverage nowadays. So what did this look like in HACMS? So we started out with building system architecture models for the vehicles that we were concerned about, produced very detailed models that captured the structure, the behavior, the interactions, the behavior of components and the system requirements, and then formally verified that the components in this architecture work together to meet our system requirements. And then we took information from those models and used that to generate component and infrastructure code and kernel configuration data, the capabilities for configuring the kernel, to configure the SEL4 separation kernel that Howie mentioned. And these are immediately, very tightly related, because the kernel now is going to guarantee that the system does only what the model says, with no other information flows or unintended memory accesses. So that the value that we get from that is that we can use our automated tools to build and check that the model of the system is correct. And then we rely on the capabilities of the SEL4 separation kernel to ensure that that's exactly what we get when we go to deploy the system. And a number of these tools that we used in the program either were funded with DARPA funding or benefited from DARPA funding, including SEL4. It wasn't created under DARPA funding, but it definitely has been improved over the years on several different DARPA programs. Okay, so this guy, the SMACM copter. SMACM was the name of our program on HACMs. But what we've got here inside the fuselage is a Pixhawk flight control computer, and that talks over a CAN bus to this TK1 mission computer that's up here in the Tupperware. It's got a little camera on the bottom for doing surveillance. It's got a laser altimeter down there, and we got a bunch of radios. That's just a safety radio to make sure we always have control of the vehicle. But we have this 3DR encrypted radio link for talking with the ground station, and bringing down telemetry and also controlling the vehicle. You can see that set up out in the lobby afterwards. And then we have a Wi-Fi link for sending down data from the camera. It just has a Wi-Fi connection that streams data down to our ground system. So 2 different radios. And that's important, but we'll get to that in a minute. So formal methods are not the easiest thing to show and demonstrate to people because it's a tool and ta-da, I did my proof and it worked. Great, that's super cool. So having vehicles like this to demonstrate these sorts of before and after capabilities is super valuable. And we did that here. We used that Wi-Fi link as a way of attacking the vehicle and showing different kinds of cyber attacks and whether we were vulnerable to them beforehand or not afterwards. Okay, so this is, if we did a flight demo here, this is what it would have looked like. This is the final demo that we did over in Sterling at a big high bay facility at then Rockwell Collins in 2017. So you see in the middle, there's sort of a mission area where the vehicle is supposed to go and fly over that and take pictures and look at the little buildings on the ground. We have good guys on the left side and the bad guys with the pirate flag on the right side, and they're going to try to take over, actually physically take control of the vehicle by attacking it while it's flying. And here's this familiar picture. But this is the before picture. And you can see we've got the flight control computer on the left and the mission computer on the right. So we start out with an unverified kernel that has some memory protection bugs that we're going to be able to exploit. Now I mentioned that our encrypted radio has some really solid encryption on it. The attackers are not going to be able to corrupt that. Instead, they take advantage of the fact that this Wi-Fi connection is kind of crappy, and they can use that to gain access to the Linux VM that's hosting our camera software. And from there, exploit a memory protection bug to access the seething pile of bits, which is the rest of the system, and identify the encryption keys, and use that as a way of then taking over that encrypted data link, taking control of the vehicle. So I will show you a little video of what that looks like in action. So the vehicle will take off and come to an initial altitude. On the left, you see the ground control station. And on the right, this is the hacker screen. This is exactly what he's doing. And so as the vehicle comes into the mission area, it starts, you can see that it's identifying, seeing the different buildings on the ground. And then the attacker will launch his exploit. He's going to log into the software on the vehicle there, the camera software, and he's launched his exploit, and he actually, this is the live memory that's in the vehicle. You can see the values changing. He does his scan of memory and identifies where the keys are for the vehicle. And as he starts to overwrite those, if you watch the ground station, you'll note that the ground station will very soon get interrupted and lose contact with the vehicle. So now the attacker, as he has the keys, he's going to use his own version of the keys to communicate securely using the same encryption system with the vehicle. He'll bring up his own version of the ground control station, and now he's taking control of the vehicle. And at this point, he'll also launch the attack on the surveillance system. So you'll see that the ground control station now has had their video stream interrupted, and in a few seconds, the attacker now has the video stream. So at this point, the attacker has control of the vehicle. He has the telemetry, he has the video, and the ground station has nothing. So attackers, you can go ahead and take the vehicle at this point and bring it into enemy territory and actually physically capture the vehicle as well. Okay, way to go, attackers. All right, so that shows you what can go wrong, the before case. All right, here's the architecture after we applied our formal methods tools. So that included using the SEL4 verified kernel, and that allows us to provide very strong, provably strong separation between all of the components. So not just this VM, but between the other, there was some 4 or 5 other components running on SEL4 on the mission computer. But that now will prevent the attacker, even though they can still gain access to the Linux VM that's hosting the, it's running our USB and talking to the camera and the Wi-Fi, but that's all it can do. And in fact, you'll see in the demo that they will, out of frustration, just crash fork bomb the VM, the camera VM, and it dies, but then we can restart it. So now let's look at the after demo and see how things go. So just like before, the good guys will take off, hover, and move into our mission area. We'll see the buildings on the camera, and the bad guys, when they're ready, will launch their same attack as before. And you see all they get is zeros. They're not able to access memory outside of the partition that was given to the camera software. So at this point, now they're going to launch their fork bomb attack. That's going to start spawning processes on the vehicle. The good guys are still in control of the vehicle, still executing their mission, but the attacker is using up more and more resources in the camera partition. So at some point, if you watch here, you'll see the camera freeze as that Linux partition crashes, but we'll restart that partition, and in a few seconds this will restore. In the meantime, you can see that the telemetry is live. We still have positive control of the vehicle. Everything is working. We're performing our mission, and now the camera has come back, and we have all of our original functionality. We're able to complete our mission. The good guys have complete control of the vehicle, like they started with, and the bad guys have nothing. So it's completely opposite where we were before. So now the good guys will finish their mission and go back to base, back in friendly territory, and land the vehicle. Okay. So that's cool. That's a toy. What about a real helicopter? Maybe like this one. So this is our Boeing unmanned Little Bird helicopter, which is, it's a real helicopter. Usually there's dudes with guns in the back there, but now it's all full of computers. Somewhere in the very middle of that picture, you'll see our friend Doug Stewart from Boeing, who's with us today, and he was the Boeing lead for this activity. But we wanted to show that you could do this on a real vehicle as well. So as was mentioned before, All the work using these same tools and applying, porting the software to run on SEL4 had to be done by the Boeing software engineers who were not formal methods experts. The blue stuff in there is all things that got re-engineered and rehosted on SEL4. If we look at the cartoon of the architecture, you can see we've got a lot of similarity here, right? We've got the telemetry link, and we've got the flight control computer and the mission computer. So in the original version of the vehicle, everything on the mission computer is running on Linux, so there's no protection between this data logging process and the camera controller and this other process that's doing route management. And the attack that we did here, instead of a remote network-based attack, was a USB physical device that can plug into this system to do data logging and maintenance. So here, the attackers inserted a bug, and this attack was designed by the red team who was here. Eric Thayer is in the room who worked on that. And that attacks the camera, and it just basically restows the camera so the thing can't do its mission. And then in the after version of this, we rehosted all the mission software on SEL4, so we were able to have separate Linux partitions doing the data logging, another one running the camera software, and then these more critical things that we're doing, the authorization and level of interactivity controller and the communication with the flight control system. Those are all things that were custom components to run on SEL4. And again, as you see, the attacker is able to corrupt the data logging partition, but can't access anything else. So here's a little video of that.
Little Bird will fly a sortie to a specified location, take reconnaissance photos, and return. But the red team will infect the helicopter with malware using a mechanic's thumb drive, usually used for diagnostics, to try to kill the mission.
I'm Brandon Haynes. I am with the red team acting as the voice of the offense on the HACMS program.
The aircraft is sitting on the ramp, the pilot goes through the startup sequence, and then the maintenance person who's already out there will take a USB cable and insert it into the USB port on the aircraft.
The virus enters Little Bird through the flight data recorder. Without HACMS, the red team is able to take control.
We are able to get into the data logger and have full control of the Little Bird's mission command systems. That means we're able to shut down the camera system or cause the helicopter to fly wherever we'd like.
Oh, I was absolutely flabbergasted that they came in and within an hour they had a control of my sensor, and I never expected them to get that far.
And if it's able to successfully do that, then the aircraft can't complete its mission because it can't use the camera.
They will fly the same sortie, now with the HACMS protection. This time, the infection is contained within the HACMS partition. It isn't able to spread beyond the data recorder to the camera or any other part of the helicopter.
In the HACMS secured Little Bird, the data logger component, which is the only component that uses that USB interface, although we're able to get into the data logger is compartmentalized off from all of the mission command components. We're able to shut down the data logger, but we are not able to tell the helicopter to fly elsewhere, and we are not able to shut down the WESCAM.
Okay, so with the last couple of minutes, let's jump ahead to now, 10 years later. And surely we've been able to take advantage of all of these new technologies in aerospace. And that's sort of true, but actually it's these folks like Mike Hicks talked about at Amazon, who are adopting and using formal methods, tools, and technologies to improve the security and reliability and performance of their systems. So how do we realize the same benefits for these kind of companies, like my company? How do we transition these same mechanisms that were demonstrated in HACMS? Well, that's part of what we're doing in the Provers program. And here you see a lot of the same characters that we had in HACMS, but also some new partners with us. And what we're focusing on there is really integrating formal methods tools into our CI/CD pipelines that are in use in real defense companies like ours. And we have a complete stack of tools that you see on the right. But again, the stuff on the top is kind of in this category of invisible formal methods where we're integrating into the architecture modeling tools and how do we specify what the components do and what the structures are and who can talk to whom. And then we use, again, SEL4, this verified exquisite artifact, and have tools that allow us to take our verified models, target the secure separation kernel, and end up with a system that has guaranteed capabilities, guaranteed resilience against these classes of cyber attacks. So again, our tools are integrated with our current workflows, and we're applying them here to a UAV that, and some mission software that has been demonstrated as part of the Army's Launched Effects program. So just we've done a demo at the end of phase 1 of Provers, where we took the mission software from the Collins Rapid Edge system, and this is a UAV that gets launched out of a tube on a helicopter, for example, and they can go and join up with 3 or 4 others, and they operate autonomously to avoid threats and make sure they cover some surveillance area. They can do all kinds of different missions like that. So, and our mission software is a collaborative mission system. So we were able to take that software and rehost it on SEL4. So now it's the same software. It's running on Linux in a partition on in a virtual machine on SEL4. So now we have complete control over the interface to that, and we can build onto that and add new capabilities, which we'll do in the subsequent phases in the program. But we've provided guaranteed isolation and control over all the input and output interfaces, and we demonstrated this with a hardware-in-the-loop simulation and showed that we could replicate the performance of the autonomous multi-UAV mission that was flown last year at the Army's Edge 24 events. And once again, all of this was done by software engineers at Collins in our mission systems business who are not formal methods experts. We showed them how to use SEL4 and showed them some examples, and they were able to take it and run. And so this is, again, this is showing this transition mechanism of taking an exquisite artifact that's had a lot of effort put into it and making use of it as the foundation of other systems. So HACMs showed that formal methods can be used to eliminate important security vulnerabilities from embedded software in real aircraft. And approvers, we're now enhancing the usability of formal methods by integrating them into our CI/CD pipelines for use by defense and aerospace engineers. And in both of these programs, we are continuing to use these 2 transition mechanisms where we reuse critical high-valued components that have been developed and verified by formal methods experts, but we also integrate formal methods tools into existing workflows so that they can be used by non-formal methods experts. But in both of these programs, we're showing that formal methods are practical and effective and can be used on real aerospace systems. Thanks a lot.
Thanks, Darren. So the future of formal methods, tools, and techniques, it's a pretty big subject, and I think I have 2 slides. So we'll say, you've already heard about some of the programs that are ongoing at DARPA. We are, again, very focused in this colloquium on transitioning the technologies and making real use of the technologies that are the risk has been taken away. But we are still looking to the future and trying to hit home runs so that in the future we're going to have a dramatic impact and be able to broaden and make wider use of these formal methods technologies. So I want to briefly mention programs that are ongoing that look to accomplish that. One you've heard about, which was the Tractor program. Rust and these memory-safe approaches to building software are great. Can we translate all of the code that's written in a language like C automatically into idiomatic Rust is a program that's ongoing. Even beyond that, a lot of the software that we're integrating is open source software that has all kinds of unusual provenances and all kinds of vulnerabilities in it. What kinds of tools can we develop that allow us to use open source software in a very reliable way, which is the focus of the EBOS program. You've heard about the Provers program, which is taking formal methods tools and integrating them into real CI/CD pipelines and using traditional, having them be as usable as possible by traditional engineers. And that's a program that's ongoing. And also, one of my personal favorites is the mixed reality program, where we're applying formal methods in a really new place that is really coming. The mixed reality systems, if you haven't seen the latest ones, they really are coming, and we need to figure out how to protect people that use them and against the exploitation of the intimate connection between people and the devices that they're using. So we are very focused on transitioning as much as possible these formal methods tools, and we're also looking to do the DARPA thing of trying to hit home runs that would have a dramatic effect in the future in this technology area. And so just to summarize what you heard several presentations that focus on transitionable technologies that are in this sort of mostly in this pioneering phase of development, where we think that they're ready to go and ready to have a big impact on real systems today. So just to wrap up, DARPA is maturing and applying formal methods to improve the resilience of computer-based systems. And we can build better systems, and we very much urgently need to. This is a pointer to formal methods on the DARPA website, where you'll see pointers to various tools that are available to you. And I'd also, if you haven't already, really encourage you to see the posters that are being presented around the corner that have 50+ organizations that want to continue to advance and make available formal methods, tools, and technologies. So with that, I would say thank you very much, and I believe we're on break.